What if the key to unlocking the secrets of the universe has been hiding in plain sight all along? Picture this: a cosmic shortcut, a tunnel through the fabric of space and time, connecting two distant points in the blink of an eye. This isn't science fiction, it's the tantalizing possibility of wormhole travel. Today, we're diving into 30 mind-bending theories about the universe's first wormhole travel, theories that could reshape everything we know about reality. From the groundbreaking ideas of Einstein and Rosen to the wild frontiers of quantum entanglement and higher dimensions, we'll explore how these cosmic tunnels might not only exist but could one day allow us to traverse the stars. So buckle up and prepare to have your mind stretched to its limits. By the end of this journey, you'll see the universe in a whole new light, and who knows? You might just uncover the answer to one of humanity's greatest questions. Are wormholes the key to our future among the stars? Let's begin. Now, let's step back in time to where it all began, the very foundation of wormhole theory. In the 1930s, Albert Einstein and his colleague Nathan Rosen proposed something extraordinary: bridges in spacetime. These weren't just any bridges, they were theoretical tunnels that could connect two distant points in the universe, bending the fabric of space and time itself. This groundbreaking idea came to be known as the Einstein-Rosen Bridge, and it laid the groundwork for everything we now understand about wormholes. Einstein and Rosen's work was rooted in the equations of general relativity, which describe how massive objects warp the space around them. They realized that under certain conditions, this warping could create a shortcut, a bridge between 2 points in spacetime. Imagine folding a piece of paper so that 2 distant dots touch. That's essentially what an Einstein-Rosen bridge does, but on a cosmic scale. At the time, these bridges were purely theoretical, and Einstein himself doubted they could ever exist in reality. But their work opened the door to a whole new way of thinking about the universe. It suggested that spacetime isn't just a static backdrop, it's dynamic, malleable, and full of possibilities. This idea became the cornerstone of modern wormhole theories, inspiring scientists to explore how these cosmic shortcuts might actually work. So, while Einstein and Rosen may not have envisioned wormholes as we think of them today, their work was the spark that ignited the fire. It showed us that the universe might be far more interconnected and far stranger than we ever imagined, and with that, the journey into the mysteries of wormholes truly began. Next, we'll explore how these theoretical bridges might become traversable, and what it would take to make wormhole travel a reality. Now, let's take a closer look at what it would actually take to make wormholes more than just a theoretical curiosity. What if they could be traversable? The idea of traveling through a wormhole is thrilling, but it's not as simple as stepping into a tunnel and popping out on the other side. For a wormhole to be stable and safe for travel, certain conditions must be met, and this is where things get truly fascinating. One of the biggest challenges is keeping a wormhole open long enough for anything or anyone to pass through. According to the math, wormholes are incredibly unstable. They tend to collapse almost instantly under the immense gravitational forces at play. But here's where exotic matter and negative energy come into the picture. Exotic matter isn't your everyday material, it's a hypothetical substance with properties that defy the laws of physics as we know them. Specifically, it has negative energy density, which means it can counteract the natural tendency of a wormhole to collapse. Think of it like this: if a wormhole is a tunnel, exotic matter acts as the scaffolding that holds it open. Without it, the tunnel would collapse in on itself before you could even take a step inside. Negative energy, on the other hand, is a bit like the glue that keeps everything in place. It's a strange and counterintuitive concept, but it's essential for stabilizing a wormhole and making it traversable. Now, here's the catch: exotic matter and negative energy are purely theoretical at this point. We've never observed them in nature, and creating them in a lab is beyond our current capabilities. But that hasn't stopped scientists from exploring the possibilities. Some theories suggest that quantum effects like the Casimir effect might produce tiny amounts of negative energy, offering a glimpse of how we could one day harness it. So, while traversable wormholes remain firmly in the realm of speculation, they're not entirely out of reach. The conditions required exotic matter, negative energy, and a deep understanding of spacetime are daunting, but they're also a reminder of how much we still have to discover about the universe. And who knows, with enough ingenuity and a bit of luck, we might one day unlock the secrets of wormhole travel. Next, we'll dive into an even more mind-bending idea: the connection between wormholes and quantum entanglement. How could the strange behavior of particles at the quantum level be linked to these cosmic shortcuts? Let's find out. Now, let's shift our focus to one of the most intriguing connections in modern physics: the relationship between quantum entanglement and wormholes. At first glance, these two concepts might seem worlds apart. Quantum entanglement deals with the behavior of tiny particles, while wormholes are cosmic shortcuts through spacetime. But what if they're actually two sides of the same coin? This is where the ER equals EPR conjecture comes into play, a bold idea that suggests a deep link between these phenomena. Quantum entanglement is a strange and fascinating feature of the quantum world. When two particles become entangled, their properties become interconnected, no matter how far apart they are. Change one particle and the other instantly responds, as if they're communicating faster than the speed of light. This phenomenon has puzzled scientists for decades, but the ER equals EPR conjecture offers a potential explanation. Entangled particles might be connected by microscopic wormholes. The name ER equals EPR comes from two groundbreaking ideas in physics. ER refers to the Einstein-Rosen Bridge, the original concept of a wormhole, while EPR stands for Einstein, Podolsky, and Rosen, who first described quantum entanglement. The conjecture proposes that every pair of entangled particles is linked by a tiny wormhole, creating a bridge between them. In other words, entanglement isn't just a mysterious connection, it's a physical one woven into the fabric of spacetime itself. This idea has profound implications. If true, it means that wormholes aren't just massive cosmic tunnels. They could also exist on the smallest scales, connecting particles across vast distances. It also suggests that the quantum world and the cosmic world might be far more intertwined than we ever imagined. But how does this work in practice? Imagine two entangled particles as the ends of a microscopic wormhole. The wormhole itself would be incredibly tiny, far smaller than an atom, and it wouldn't allow for any physical travel. Instead, it would act as a conduit for information, explaining how entangled particles can influence each other instantaneously. Of course, this is still a theoretical idea, and proving it is no small task. Detecting microscopic wormholes or directly observing their effects on entangled particles is beyond our current technology. But the ER equals EPR conjecture has sparked a wave of excitement in the physics community, offering a new way to think about the connections between quantum mechanics and general relativity. As we continue to explore this idea, one thing is clear: the universe is far stranger and more interconnected than we ever imagined. And who knows, the key to unlocking the mysteries of wormholes might lie in the quantum realm, hidden within the behavior of the tiniest particles. Next, we'll take a step into the realm of time travel as we explore the idea of wormholes as potential time machines. Could these cosmic shortcuts allow us to journey through time as well as space? Let's find out. Now, let's venture into one of the most mind-bending possibilities of wormholes: their potential to act as time machines. Imagine stepping through a cosmic shortcut not just to another part of the universe, but to another point in time. This idea isn't just science fiction, it's a concept rooted in the equations of general relativity. To understand how wormholes could enable time travel, we need to revisit the nature of spacetime. According to Einstein's theory, massive objects like stars and black holes warp spacetime, creating curves and bends. A wormhole, in essence, is a shortcut through this warped fabric connecting two distant points. But here's where it gets fascinating. If one end of a wormhole were moved at near light speeds or placed near an intense gravitational field, time would pass differently at each end. This phenomenon, known as time dilation, means that the two ends of the wormhole could exist in different moments in time. For example, if you entered one end of the wormhole, you might emerge from the other end not just in a different location, but in a different year or even a different century. In theory, this could allow for travel into the past or future, depending on how the wormhole is configured. But before we start packing our bags for a trip to the age of dinosaurs, there's a catch. Time travel through wormholes comes with a host of paradoxes and challenges. One of the most famous is the grandfather paradox. If you traveled back in time and prevented your grandparents from meeting, how could you exist to make the journey in the first place? This paradox highlights the logical inconsistencies that arise when we consider altering the past. Another challenge is the stability of wormholes themselves. As we've discussed earlier, keeping a wormhole open requires exotic matter or negative energy, which we haven't yet discovered. Even if we could stabilize a wormhole, the extreme conditions needed to create time dilation, like near light speed travel or proximity to a black hole, are far beyond our current capabilities. Despite these hurdles, the idea of wormholes as time machines continues to captivate scientists and dreamers alike. It raises profound questions about the nature of time, causality, and the universe itself. Could the laws of physics allow for such journeys, or are they strictly forbidden? And if time travel were possible, what would it mean for our understanding of reality? As we ponder these questions, one thing is certain: the universe is full of mysteries that challenge our imagination. Wormholes, whether as cosmic shortcuts or time machines, remind us that the boundaries of space and time are far more fluid than we once thought. Next, we'll explore an even more enigmatic idea: the possibility that wormholes could exist within black holes, serving as gateways to other regions of spacetime. What secrets might these cosmic giants hold? Let's dive in. Now, let's turn our attention to one of the most intriguing and mysterious places in the universe: black holes. These cosmic giants, with their immense gravitational pull, have long fascinated scientists and science fiction fans alike. But what if black holes aren't just destructive forces? What if they hide something extraordinary within them, like wormholes? The idea that wormholes could exist inside black holes is a theory that pushes the boundaries of our understanding of spacetime. According to this concept, the intense gravitational forces at the heart of a black hole might create the conditions necessary for a wormhole to form. In this scenario, a black hole wouldn't just be a one-way ticket to oblivion. It could serve as a gateway to another part of the universe, or even another universe entirely. To understand how this might work, let's revisit what happens near a black hole. As matter gets pulled into a black hole, it's stretched and compressed in a process known as spaghettification. At the very center lies the singularity, a point where gravity becomes infinitely strong and the laws of physics as we know them break down. But some theories suggest that instead of a singularity, there could be a wormhole, a tunnel through spacetime that connects two distant regions. This idea is supported by certain solutions to Einstein's equations of general relativity. For example, the Einstein-Rosen Bridge, which we discussed earlier, describes a theoretical connection between two black holes. If such a bridge exists, it could allow for travel between these points, effectively creating a cosmic shortcut. However, exploring this theory comes with significant challenges. The environment near a black hole is one of the most extreme in the universe. The gravitational forces are so strong that not even light can escape, making it nearly impossible to observe what's happening inside. Additionally, the intense radiation and tidal forces near a black hole would make any attempt to approach it, let alone enter it, extremely dangerous, if not outright impossible with our current technology. Another major hurdle is the question of stability. Even if a wormhole exists within a black hole, it would likely be incredibly unstable. The same forces that create the wormhole could also destroy it almost instantly, making it useless for travel. And as we've discussed before, stabilizing a wormhole would require exotic matter or negative energy, which we have yet to discover or understand fully. Despite these challenges, the idea of wormholes in black holes continues to inspire both scientific research and imaginative speculation. It raises profound questions about the nature of spacetime, the limits of our knowledge, and the possibilities that lie beyond the event horizon. Could black holes truly be gateways to other realms, or are they simply cosmic dead ends? As we continue to explore the mysteries of the universe, one thing is clear: black holes and wormholes represent some of the most fascinating and enigmatic phenomena in existence. They challenge us to think beyond the limits of our current understanding and imagine what might be possible in the vast, uncharted reaches of spacetime. Next, we'll delve into another captivating theory: the role of dark matter in the formation or stabilization of wormholes. Could this mysterious substance hold the key to unlocking the secrets of cosmic shortcuts? Let's find out. Now, shifting our focus to another cosmic mystery, let's explore the intriguing connection between wormholes and dark matter. While dark matter remains one of the most elusive substances in the universe, its potential role in the formation or stabilization of wormholes opens up a fascinating realm of possibilities. Dark matter, as you may know, is an invisible form of matter that doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. Yet, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Scientists estimate that dark matter makes up about 85% of the universe's total matter, dwarfing the amount of ordinary matter we can see. So, how could dark matter be linked to wormholes? One hypothesis suggests that dark matter's gravitational influence might play a crucial role in shaping spacetime in ways that could facilitate the creation of wormholes. Imagine dark matter as a kind of cosmic scaffolding, subtly bending and warping spacetime on a massive scale. In regions where dark matter is densely concentrated, its gravitational pull could potentially create the conditions necessary for a wormhole to form. Another intriguing idea is that dark matter might help stabilize wormholes. As we've discussed earlier, wormholes are notoriously unstable, often collapsing almost instantly after forming. Exotic matter or negative energy is thought to be required to keep them open, but what if dark matter could provide a similar function? Some theories propose that dark matter's unique properties might counteract the forces that cause wormholes to collapse, effectively acting as a cosmic glue that holds these space-time tunnels together. Of course, this is all speculative at this point. Dark matter itself is still poorly understood, and its exact nature remains one of the biggest unsolved mysteries in physics. We don't yet know how it interacts with ordinary matter or space-time, let alone whether it could influence wormholes. However, the possibility is tantalizing. If dark matter does play a role in wormhole formation or stabilization, it could revolutionize our understanding of both these cosmic phenomena and the universe as a whole. This theory also raises exciting questions about the nature of dark matter itself. Could it be more than just a passive gravitational force? Could it have properties we haven't yet discovered that make it a key player in the cosmic architecture of spacetime? Exploring these ideas could lead to groundbreaking discoveries, not just about wormholes, but about the fundamental structure of the universe. As we continue to probe the mysteries of dark matter and wormholes, one thing is certain: the interplay between these two enigmatic concepts offers a wealth of opportunities for scientific exploration and imaginative speculation. Whether dark matter holds the key to unlocking the secrets of wormholes or not, Its study is sure to deepen our understanding of the cosmos in ways we can't yet fully imagine. Next, we'll venture into the realm of higher dimensions, where wormholes might exist beyond the three-dimensional space we're familiar with. Could these higher dimensional wormholes be the ultimate cosmic shortcuts? Let's find out. Now, let's take a step beyond the familiar dimensions of space and time and venture into the realm of higher dimensions. What if wormholes aren't confined to the three-dimensional world we know? What if they exist in dimensions we can't even perceive? This is where string theory and M-theory come into play, offering a mind-bending perspective on the nature of wormholes. String theory, one of the most ambitious frameworks in modern physics, suggests that the universe isn't just made up of the three spatial dimensions we experience: length, width, and height, but rather, it could have as many as 10 or even 11 dimensions. These extra dimensions are thought to be compactified or curled up at such tiny scales that they're invisible to us. But here's where it gets fascinating. These hidden dimensions might be the key to understanding wormholes in a whole new way. According to string theory, higher dimensional wormholes could exist as bridges not just through space, but through these additional dimensions as well. Imagine a wormhole not as a tunnel through our three-dimensional space, but as a passage that twists and turns through dimensions we can't see. This idea opens up the possibility that wormholes could connect distant parts of the universe in ways that defy our conventional understanding of distance and time. M-theory, an extension of string theory, takes this concept even further. It proposes that our universe might be just one of many membranes or brains floating in a higher dimensional space. In this framework, wormholes could serve as connections not just between points in our universe, but between entirely different brains, essentially linking parallel universes. Picture a wormhole as a cosmic doorway, not just to another galaxy, but to an entirely different reality. But how could we ever detect or interact with these higher dimensional wormholes? The answer lies in the mathematics of these theories, which suggest that the effects of higher dimensional wormholes might still leave traces in our three-dimensional world. For example, gravitational waves or other exotic phenomena could provide clues about their existence. While we don't yet have the technology to explore these ideas experimentally, the theoretical groundwork laid by string theory and M-theory offers a tantalizing glimpse into what might be possible. This theory also raises profound questions about the nature of reality itself. If higher dimensional wormholes exist, what does that mean for our understanding of space, time, and the universe? Could these hidden dimensions hold the key to unlocking the ultimate cosmic shortcuts? As we continue to explore these ideas, one thing is clear: the universe is far stranger and more complex than we ever imagined. Next, we'll dive into the concept of the multiverse and explore how wormholes might connect not just different regions of space, but entirely different universes. Are we living in just one of countless parallel realities? Let's find out. Now, let's shift our focus to an even more mind-bending idea. What if wormholes aren't just shortcuts through our universe, but gateways to entirely different universes? This brings us to the concept of the multiverse, a theory that suggests our universe might be just one of countless parallel realities. And if that's true, could wormholes be the bridges that connect them? The multiverse theory has gained traction in recent years, with various cosmological models proposing that our universe is part of a vast, interconnected web of universes. Each of these universes could have its own unique set of physical laws, constants, and even dimensions. But how would wormholes fit into this picture? One possibility is that wormholes could serve as cosmic tunnels linking these parallel realities. Imagine a wormhole not just as a shortcut through space, but as a portal to an entirely different universe. In this scenario, traveling through a wormhole could take you to a place where the laws of physics are completely different, where gravity might be stronger, time might flow backward, or even where life as we know it could exist in forms we can't even imagine. This idea ties into the concept of brane worlds, which we touched on earlier with M-theory. If our universe is a membrane floating in a higher dimensional space, wormholes could connect our brain to others, creating pathways between universes. These connections might not be stable or easy to navigate, but they open up the tantalizing possibility that the multiverse isn't just a theoretical construct. It could be a tangible reality, with wormholes as the key to exploring it. But how does this fit into our current understanding of cosmology? Some models suggest that the multiverse could have formed during the Big Bang, when rapid expansion created bubbles of spacetime that evolved into separate universes. If wormholes existed in the early universe, they might have connected these bubbles, leaving behind a network of cosmic shortcuts. Of course, the idea of traveling to another universe raises all sorts of questions. Would it even be possible to survive such a journey? What would happen if the laws of physics in another universe were incompatible with our own? And if wormholes do connect universes, could they also allow for the transfer of information or even life between them? While these questions remain unanswered, the theory of wormholes and the multiverse offers a fascinating glimpse into the possibilities of cosmic exploration. It challenges us to think beyond the boundaries of our own universe and consider the idea that we might be part of something far grander and more interconnected than we ever imagined. Next, we'll explore another intriguing theory. Could wormholes be formed from cosmic strings, those hypothetical one-dimensional defects in spacetime? And if so, what would that mean for our understanding of the universe? Let's dive in. Now, let's turn our attention to a theory that takes us into the realm of the ultra-exotic wormholes as cosmic strings. Cosmic strings are hypothetical one-dimensional defects in spacetime, often described as incredibly thin, incredibly dense threads stretching across the universe. These cosmic strings are thought to have formed in the early universe during a phase transition when the cosmos was cooling down. But how could these bizarre structures be connected to wormholes? The idea is that cosmic strings, with their immense gravitational pull, could warp spacetime so dramatically that they create shortcuts through the fabric of the universe. Picture a cosmic string as a thread so dense and heavy that it bends spacetime around it, forming a kind of tunnel. If two cosmic strings were to interact or loop around each other, they might create a stable passage, a wormhole connecting distant regions of space. This theory is particularly intriguing because it suggests that wormholes might not require exotic matter or negative energy to stay open, as some other theories propose. Instead, the sheer gravitational influence of cosmic strings could be enough to keep a wormhole stable. This would make cosmic string-based wormholes a more plausible candidate for real-world cosmic shortcuts, at least in theory. But what would these wormholes look like? If cosmic strings are as thin as predicted, the wormholes they create might be incredibly narrow, perhaps even microscopic. This raises questions about whether anything or anyone could actually travel through them. Could we somehow harness these cosmic strings to create larger, more navigable wormholes? Or would they remain forever out of reach, tantalizing us with the possibility of shortcuts we can never use? Another fascinating aspect of this theory is its connection to the early universe. If cosmic strings formed shortly after the Big Bang, they might have left behind a network of wormholes scattered throughout the cosmos. These ancient wormholes could still exist today, hidden in the vastness of space, waiting to be discovered. Of course, cosmic strings themselves have never been directly observed, and their existence remains purely theoretical. But if they do exist, and if they can indeed form wormholes, they could revolutionize our understanding of the universe. They might not only provide shortcuts through space, but also offer clues about the conditions of the early universe and the fundamental nature of spacetime itself. As we continue to explore the mysteries of wormholes, the idea of cosmic strings adds another layer of intrigue to the puzzle. Could these elusive threads hold the key to unlocking the secrets of the cosmos? Next, we'll explore another captivating theory. What if wormholes are connected to white holes, the theoretical opposites of black holes? And what would that mean for our understanding of spacetime? Let's dive in. Now, let's shift our focus to a theory that flips the script on what we know about black holes, wormholes, and their connection to white holes. White holes are often described as the theoretical opposites of black holes. While black holes are known for pulling everything in, even light, white holes are thought to do the exact opposite. They push everything out, allowing nothing to enter. But how do these two cosmic phenomena connect, and what role could wormholes play in this relationship? Imagine a wormhole as a bridge between a black hole and a white hole. The black hole, with its immense gravitational pull, could serve as the entrance, while the white hole acts as the exit, spewing out matter and energy on the other side. This creates a fascinating possibility, a one-way tunnel through space-time where anything that enters the black hole could emerge from the white hole in a completely different part of the universe. This idea raises some intriguing questions. For instance, if a wormhole connects a black hole to a white hole, what happens to the matter that enters? Does it get stretched, compressed, or transformed in some way as it travels through the wormhole? And if white holes are constantly expelling matter, could we detect them by observing unusual bursts of energy in space? One of the most compelling aspects of this theory is how it challenges our understanding of spacetime. Black holes are already mysterious enough, but adding white holes and wormholes into the mix creates a cosmic puzzle that could reshape our view of the universe. If wormholes truly link black holes to white holes, they might not just be shortcuts through space. They could also be pathways through time, offering a glimpse into the far reaches of the cosmos. However, there's a catch. White holes, like wormholes, remain purely theoretical. No one has ever observed a white hole, and their existence is still a matter of debate among scientists. Some theories suggest that white holes could be the remnants of black holes that have reached the end of their life cycle, while others propose that they might exist in regions of the universe we have yet to explore. Despite the uncertainty, the idea of wormholes connecting black holes to white holes is a captivating one. It opens up new possibilities for understanding the universe's most extreme environments and the strange ways in which spacetime can bend and twist. Could these cosmic tunnels be the key to unlocking the secrets of the universe? Or are they simply another fascinating piece of the puzzle, waiting for us to uncover more clues? As we continue our journey through the mysteries of wormholes, let's turn our attention to another mind-bending theory. What if wormholes played a role in the Big Bang itself? Could they have shaped the early universe in ways we're only beginning to understand? Let's explore this next. Now, let's take a step back in time, way back to the very beginning of everything. The Big Bang is often described as the moment when the universe burst into existence. But what if wormholes played a role in shaping the cosmos from its earliest moments? This theory suggests that wormholes could have formed during the Big Bang, creating connections between different regions of the rapidly expanding universe. Imagine the universe in its infancy, a hot, dense soup of energy and matter. As space itself stretched and expanded, tiny fluctuations in this primordial chaos could have given rise to wormholes. These cosmic tunnels might have acted as bridges, linking distant parts of the universe before they had even fully formed. If this is true, wormholes could have been instrumental in distributing matter and energy more evenly, helping to create the large-scale structure of the universe we see today. But what does this mean for our understanding of the universe's origins? If wormholes existed in the early universe, they could provide clues about how the cosmos evolved. For instance, they might explain why certain regions of the universe appear so uniform, even though they are billions of light years apart. This idea ties into the concept of cosmic inflation, the rapid expansion of space that occurred just after the Big Bang. Wormholes could have played a role in smoothing out the universe, ensuring that matter and energy were distributed more evenly. Another intriguing possibility is that these early wormholes might still exist today, hidden within the fabric of spacetime. If they do, they could be relics of the universe's birth, offering us a glimpse into the conditions that existed at the dawn of time. Detecting such wormholes, however, would be an enormous challenge. They would likely be incredibly small, perhaps even microscopic, and their effects on the surrounding space might be nearly impossible to observe directly. This theory also raises questions about the nature of time itself. If wormholes connected different regions of the early universe, could they have also linked different moments in time? Some scientists speculate that these primordial wormholes might have allowed for a kind of cosmic communication, enabling information to travel across vast distances almost instantaneously. This could have profound implications for our understanding of causality and the flow of time. While the idea of wormholes forming during the Big Bang is still speculative, it opens up exciting new avenues for exploring the universe's origins. By studying the potential role of wormholes in the early cosmos, we might uncover new insights into how the universe began and how it evolved into the complex, interconnected web of galaxies we see today. As we continue to unravel the mysteries of wormholes, let's turn our attention to another fascinating concept. What if wormholes are part of a quantum foam, constantly bubbling up and disappearing at the smallest scales of spacetime? Let's dive into that next. Now let's zoom in way in to the tiniest scales of the universe, where the fabric of spacetime itself becomes a bubbling, frothy sea of activity. This is the realm of quantum foam, a mind-bending concept that suggests spacetime isn't smooth and continuous as we often imagine, but instead a chaotic, ever-changing landscape at the smallest possible scales. At this level, spacetime is thought to be made up of tiny, fluctuating bubbles, constantly forming and collapsing. These bubbles are so small that they exist at the Planck scale, the smallest meaningful length in the universe. It's here, in this quantum foam, that some scientists believe wormholes might be constantly popping in and out of existence. Imagine spacetime as a bubbling pot of water, with tiny wormholes forming like fleeting bubbles on the surface. These microscopic wormholes wouldn't last long. They'd appear and disappear in an instant, far too quickly for us to detect directly. But their existence could have profound implications for our understanding of the universe. One of the most intriguing ideas is that these tiny wormholes might serve as shortcuts through spacetime, connecting distant points in ways we can't yet fully comprehend. While they're too small and unstable for anything to travel through, they could still play a role in the fundamental structure of the cosmos. For instance, they might help explain how information or energy is transferred at the quantum level, or even how particles interact across vast distances. This concept also ties into the idea of quantum entanglement, where particles become linked in such a way that the state of one instantly affects the state of another, no matter how far apart they are. Some scientists speculate that these entangled particles might be connected by microscopic wormholes, providing a physical explanation for their mysterious connection. But here's the catch: studying quantum foam and these fleeting wormholes is incredibly challenging. The scales involved are so small that they're far beyond our current ability to observe directly. Instead, scientists rely on theoretical models and mathematical predictions to explore this strange, frothy realm. Despite the challenges, the idea of wormholes in quantum foam opens up exciting possibilities. It suggests that spacetime itself might be far more dynamic and interconnected than we ever imagined. And while these tiny wormholes might not be the cosmic shortcuts we dream of for interstellar travel, they could still hold the key to understanding some of the deepest mysteries of the universe. As we ponder the implications of quantum foam and its fleeting wormholes, let's shift our focus to another fascinating idea. What if wormholes are more than just cosmic shortcuts? What if they're part of a holographic universe, encoding information about the cosmos in ways we're only beginning to understand? That's where we're headed next. Now, let's take a step into a realm where the universe itself might be a kind of cosmic projection, a hologram. This is the essence of the holographic principle, a groundbreaking idea that suggests all the information in a volume of space can be thought of as encoded on a boundary to that space, like a two-dimensional surface. It's a concept that turns our understanding of reality on its head, and when we bring wormholes into the picture, things get even more fascinating. The holographic principle emerged from studies of black holes and their event horizons, where scientists realized that the information about everything that falls into a black hole might be stored on its surface rather than lost forever. This idea was later extended to the entire universe, proposing that our three-dimensional reality could be a projection of information stored on a two-dimensional surface. So, where do wormholes fit into this? Some theories suggest that wormholes might be the bridges that connect these lower dimensional surfaces, acting as conduits for the flow of information. Imagine the universe as a vast, interconnected network, with wormholes serving as the threads that stitch together different regions of this holographic fabric. This idea has profound implications. If wormholes are part of a holographic universe, they might not just be shortcuts through space and time. They could also be the mechanisms that allow information to be shared and stored across the cosmos. In this view, a wormhole could be like a cosmic USB drive, encoding and transferring data between different parts of the universe. But how does this work in practice? One possibility is that wormholes could link different regions of spacetime in such a way that the information on one side is mirrored or encoded on the other. This could explain how entangled particles, for example, seem to communicate instantaneously across vast distances. They might be connected by microscopic wormholes that act as information highways. The holographic principle also raises questions about the nature of reality itself. If our universe is a projection, then what lies beyond the hologram? Could wormholes provide a glimpse into that deeper layer of existence? While these questions remain speculative, they open up exciting avenues for exploration, blending the worlds of quantum mechanics, general relativity, and information theory. As we wrap up this mind-bending journey into holography and wormholes, let's turn our attention to another intriguing possibility. What if wormholes aren't just isolated phenomena, but part of vast networks that span the cosmos? That's where we're headed next. Now, let's shift our focus to a concept that could revolutionize how we think about the cosmos: wormhole networks. Imagine a universe where wormholes aren't just isolated tunnels through space-time, but part of an intricate web connecting distant stars, galaxies, and even entire regions of the universe. This idea takes the concept of wormholes to a whole new level, suggesting that these cosmic shortcuts could form vast, interconnected networks. If such networks exist, they could serve as the ultimate highways for interstellar travel. Instead of spending thousands or even millions of years traveling between stars, civilizations might use wormhole networks to traverse the universe in a fraction of the time. Picture this: a spaceship enters a wormhole near Earth and emerges near a star system hundreds of light years away, all within moments. The implications for exploration, colonization, and even communication are staggering. But how could such networks form? One possibility is that wormholes are naturally occurring structures created during the early moments of the universe. As spacetime expanded, these wormholes could have stretched and connected, forming a lattice-like network. Alternatively, advanced civilizations might have engineered these networks, using their understanding of physics to create stable, navigable wormholes. Communication across these networks could also transform our understanding of the universe. If wormholes can transmit information instantaneously, they could serve as cosmic communication channels, allowing civilizations to share knowledge and coordinate across vast distances. This could explain how hypothetical alien societies might stay connected despite being separated by light years of space. Of course, the idea of wormhole networks raises plenty of questions. How would such networks remain stable over billions of years? What kind of energy or technology would be required to maintain them? And if they do exist, why haven't we detected them yet? While these questions remain unanswered, the possibility of wormhole networks opens up exciting avenues for both scientific research and imaginative speculation. As we ponder the potential of these cosmic highways, let's turn our attention to another fascinating question. Could wormholes hold the key to solving one of the greatest mysteries in astronomy, the Fermi paradox? That's where we're headed next. Now, let's take a step into one of the most intriguing questions in astronomy, the Fermi paradox. If the universe is so vast and filled with countless stars and planets, why haven't we encountered any signs of intelligent life? Could wormholes hold the answer to this cosmic mystery? The Fermi paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for their existence. One possible explanation is that advanced civilizations might be using wormholes for interstellar travel and communication, making their presence undetectable to us. Imagine a scenario where highly advanced alien societies have mastered the technology to create and maintain stable wormholes. Instead of traveling through space at sublight speeds, which would take thousands or even millions of years, they could use wormholes to zip across the universe almost instantaneously. This would allow them to explore, colonize, and communicate without leaving the kind of detectable traces we're currently searching for, like radio signals or spacecraft debris. But here's the twist. If wormholes are being used on such a grand scale, why haven't we stumbled upon any evidence of them? One possibility is that these wormholes are so advanced and efficient that they operate in ways we can't yet detect or understand. They might exist in higher dimensions, use exotic forms of energy, or be hidden in regions of space-time that are beyond our current observational capabilities. Another angle to consider is that these civilizations might be intentionally avoiding contact. If wormholes allow for instantaneous travel and communication, advanced societies could be observing us from a distance, choosing not to interfere until we reach a certain level of technological or social development. This idea ties into the concept of a cosmic zoo, where humanity is being studied but not yet engaged. The implications for the search for extraterrestrial intelligence, or SETI, are profound. If wormholes are the key to interstellar travel, our current methods of searching for alien life might be missing the mark entirely. Instead of looking for radio waves or distant spacecraft, we might need to focus on detecting the subtle signatures of wormholes, gravitational anomalies, exotic energy patterns, or even microscopic fluctuations in spacetime. While this theory is speculative, it offers a fascinating perspective on the Fermi paradox. It challenges us to rethink how we search for intelligent life and consider that the answers might lie in the very fabric of spacetime itself. As we continue to explore the mysteries of wormholes, we might just uncover clues that bring us closer to solving one of the universe's greatest enigmas. Next, we'll dive into another mind-bending idea. Could wormholes produce detectable gravitational waves? That's where we're headed next. Now, let's shift our focus to another fascinating possibility. Could wormholes leave behind traces in the form of gravitational waves? Gravitational waves, ripples in the fabric of spacetime caused by massive cosmic events like black hole mergers, have already revolutionized our understanding of the universe. But what if these waves could also reveal the presence of wormholes? The idea here is that wormholes, if they exist, might produce unique gravitational wave signatures. Unlike the waves generated by black holes or neutron stars, which are typically sharp and short-lived, wormholes could create more subtle, oscillating patterns. These patterns might arise from the way wormholes warp spacetime, potentially causing ripples that propagate outward and reach our detectors. So, how could we detect these signals? Future observatories like the Laser Interferometer Space Antenna, or LISA, which is set to launch in the next decade, could play a crucial role. LISA will be capable of detecting lower-frequency gravitational waves, which are exactly the kind of signals that wormholes might produce. By analyzing these waves, scientists could look for anomalies patterns that don't match the typical signatures of black holes or neutron stars. These anomalies might point to the existence of wormholes. But detecting these signals won't be easy. Wormholes, if they exist, are likely to be incredibly rare and located far beyond our current observational reach. Plus, their gravitational wave signatures might be faint, requiring highly sensitive instruments and advanced data analysis techniques to identify them. However, if we do manage to detect such signals, it would be a groundbreaking discovery, offering the first direct evidence of wormholes and opening up entirely new avenues for exploring the universe. This theory also raises an intriguing question. Could wormholes themselves be sources of gravitational waves? If a wormhole were to form, collapse, or interact with other massive objects, it might generate waves that carry information about its structure and properties. Studying these waves could give us insights into the nature of wormholes, how they form, how they're stabilized, and whether they could ever be used for travel. As we continue to refine our gravitational wave detectors and expand our understanding of spacetime, the search for wormhole signatures will remain an exciting frontier in astrophysics. The possibility of detecting these cosmic shortcuts through their gravitational fingerprints is a tantalizing prospect, one that could bring us closer to unraveling some of the universe's deepest mysteries. Next, we'll explore another intriguing connection: how the Casimir effect, a quantum phenomenon, might play a role in stabilizing wormholes. That's where we're headed next. Now, let's turn our attention to a fascinating quantum phenomenon that might hold the key to stabilizing wormholes: the Casimir effect. This effect, first predicted in the late 1940s, arises from the strange behavior of vacuum energy in quantum physics. At its core, the Casimir effect describes how two uncharged parallel metal plates placed extremely close together in a vacuum will experience an attractive force. This force isn't due to gravity or electromagnetism, but rather the fluctuations of quantum fields in the empty space between the plates. So, how does this relate to wormholes? One of the biggest challenges in wormhole physics is keeping them open and stable. According to general relativity, wormholes would collapse almost instantly under their own gravitational pull unless something counteracts that force. This is where exotic matter or negative energy comes into play, substances that defy the usual rules of physics by having negative mass or energy. The Casimir effect, with its ability to produce negative energy in the vacuum of space, might just provide the solution. Imagine this: if we could harness the Casimir effect on a much larger scale, it might generate enough negative energy to stabilize a wormhole's throat, preventing it from collapsing. While the effect is typically observed on microscopic scales, some theories suggest that advanced civilizations or future technologies could amplify it to macroscopic levels. This would require manipulating space-time in ways we can barely imagine today, but the potential is mind-boggling. The connection between the Casimir effect and wormholes also ties into the broader concept of vacuum energy. In quantum field theory, empty space isn't truly empty. It's teeming with virtual particles that pop in and out of existence. These fluctuations create a background energy that permeates the universe. If we could tap into this energy, it might not only stabilize wormholes but also provide insights into the fundamental nature of spacetime itself. Of course, there are significant hurdles to overcome. The Casimir effect is incredibly weak at human scales, and scaling it up to stabilize a wormhole would require technology far beyond our current capabilities. Additionally, the precise mechanisms for transferring this energy to a wormhole's structure remain purely theoretical. But the idea is compelling, offering a potential bridge between quantum mechanics and general relativity, two pillars of modern physics that have yet to be fully unified. As we continue to explore the mysteries of quantum physics and spacetime, the Casimir effect stands out as a promising avenue for understanding and potentially stabilizing wormholes. It's a reminder that even the smallest quantum phenomena could have profound implications for the cosmos. Next, we'll dive into another groundbreaking concept: how wormholes might intersect with the Alcubierre drive, a theoretical method for faster-than-light travel. Stay tuned as we explore this exciting connection. Now, let's shift gears and explore another groundbreaking idea that could revolutionize our understanding of space travel: the Alcubierre drive. Proposed by physicist Miguel Alcubierre in the 1990s, this theoretical concept offers a way to achieve faster-than-light travel without breaking the laws of physics as we know them. At its heart, the Alcubierre drive relies on the same fundamental principle as wormholes: the warping of spacetime. The Alcubierre drive works by creating a warp bubble around a spacecraft. Inside this bubble, spacetime will be compressed in front of the ship and expanded behind it, effectively allowing the ship to ride a wave of distorted spacetime. This means the ship itself wouldn't be moving through space at all. Instead, space itself would be moving around the ship. It's a bit like surfing on a cosmic wave, where the wave does all the work while you stay perfectly still. So, how does this connect to wormholes? Both concepts rely on manipulating spacetime to achieve what seems impossible. Wormholes create shortcuts through spacetime by bending it into a tunnel-like structure, while the Alcubierre drive warps spacetime to propel a ship faster than light. In both cases, the key ingredient is exotic matter or negative energy, which would be needed to stabilize the warp bubble or keep a wormhole open. Interestingly, the Alcubierre drive and wormholes might even complement each other. Imagine a scenario where a warp bubble could be used to create or stabilize a wormhole, or where a wormhole could serve as a starting point for a warp journey. The possibilities are as vast as the universe itself, and they highlight the interconnected nature of these two revolutionary ideas. However, like wormholes, the Alcubierre drive faces significant challenges. The amount of exotic matter or negative energy required to create a warp bubble is staggering, far beyond anything we can currently produce or even imagine. There are also concerns about the stability of the bubble and the potential for catastrophic effects, such as the release of massive amounts of energy when the bubble collapses. Despite these hurdles, the Alcubierre drive remains a tantalizing possibility. It's a reminder that the universe is full of mysteries waiting to be unlocked, and that the boundaries of what we consider possible are constantly being pushed. As we continue to explore the frontiers of physics, the relationship between wormholes and the Alcubierre drive offers a glimpse into a future where the stars might not be as far away as they seem. Next, we'll delve into another intriguing theory: how wormholes might hold the key to resolving one of the most perplexing puzzles in physics, the black hole information paradox. Stay tuned as we uncover the connections between these cosmic shortcuts and the fate of information in the universe. Now, let's turn our attention to one of the most puzzling mysteries in modern physics, the black hole information paradox, and how wormholes might hold the key to solving it. At the heart of this paradox is a fundamental question: what happens to information when it falls into a black hole? According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this rule by trapping everything that crosses their event horizon, including light. This contradiction has baffled scientists for decades, but wormholes might offer a way out. The idea is that information swallowed by a black hole doesn't just vanish, it could escape through a wormhole. Imagine a black hole as a cosmic vacuum cleaner, sucking in everything in its path. But instead of being lost forever, the information could travel through a hidden tunnel, a wormhole, and emerge somewhere else in the universe. This would preserve the integrity of quantum mechanics, ensuring that no information is ever truly destroyed. It's like dropping a letter into a mailbox and having it reappear in another mailbox halfway across the world, completely intact. This theory ties into the concept of the ER equals EPR conjecture, which suggests a deep connection between wormholes and quantum entanglement. In this framework, particles entangled across vast distances might be linked by microscopic wormholes. If this is true, then the information falling into a black hole could be entangled with particles outside of it, effectively creating a pathway for the information to escape. It's a mind-bending idea that bridges the gap between quantum mechanics and general relativity, two fields that have long struggled to coexist. However, there's a catch. For this to work, the wormhole would need to be stable and accessible, which brings us back to the challenges we've discussed earlier: exotic matter, negative energy, and the extreme conditions required to keep a wormhole open. Even if such a wormhole exists, detecting it or proving its role in resolving the information paradox would be an enormous scientific undertaking. But the possibility alone is enough to spark excitement and curiosity, as it hints at a universe far more interconnected and mysterious than we ever imagined. As we continue to explore the frontiers of physics, the relationship between wormholes and the black hole information paradox reminds us that the universe is full of surprises. It challenges us to think beyond the limits of our current understanding and to consider that even the most perplexing problems might have solutions hidden in the fabric of spacetime itself. Next, we'll explore how wormholes might challenge our understanding of time itself, diving into the theory that these cosmic shortcuts could allow for backward time travel. Stay tuned as we unravel the implications of wormholes on the arrow of time. Now, let's shift our focus to one of the most intriguing possibilities wormholes present: their potential to challenge our understanding of time itself. Specifically, we're diving into the theory that wormholes could allow for backward time travel, turning the arrow of time on its head. The arrow of time is a concept that describes the one-way flow of time from the past to the future. It's why we remember yesterday but not tomorrow, and why a broken glass doesn't spontaneously reassemble itself. But what if wormholes could bend or even reverse this flow? The idea isn't as far-fetched as it might sound. According to some theories, traversing a wormhole could create a pathway not just through space but through time as well. Imagine a wormhole connecting 2 points in spacetime. If one end of the wormhole were accelerated to near light speeds or placed in a strong gravitational field, time would pass more slowly for that end compared to the other. This difference in the passage of time could create a scenario where entering one end of the wormhole would allow you to exit the other end at an earlier moment in time. In essence, you could travel backward along the timeline, defying the conventional arrow of time. This concept ties into the idea of closed time-like curves, hypothetical paths through spacetime that loop back on themselves. If a wormhole were to form such a curve, it could theoretically enable time travel to the past. However, this raises a host of paradoxes, the most famous being the grandfather paradox. What happens if you travel back in time and prevent your own existence? While these paradoxes are mind-bending, they also highlight the profound implications of wormholes on our understanding of time. Of course, the challenges are immense. Stabilizing a wormhole for time travel would require exotic matter or negative energy, and the conditions needed to create such a scenario are far beyond our current technological capabilities. But the theoretical possibility alone opens up a universe of questions. Could wormholes be the key to unlocking the mysteries of time? And if so, what would that mean for our understanding of cause and effect, free will, and the very nature of reality? As we ponder these questions, it's clear that wormholes don't just challenge our understanding of space, they force us to rethink time itself. The arrow of time, once thought to be an unbreakable rule, might not be as rigid as we once believed. And that's a thought worth exploring further. Next, we'll delve into the anthropic principle and how the existence of wormholes might be tied to the very nature of our universe. Stay with us as we uncover yet another layer of this cosmic mystery. Now, let's turn our attention to a fascinating intersection of cosmology and philosophy, the anthropic principle and its potential connection to wormholes. The anthropic principle suggests that the universe must have the properties it does because if it didn't, we wouldn't be here to observe it. In other words, the conditions of the universe are finely tuned to allow for the existence of life. But what does this have to do with wormholes? Let's explore. If wormholes exist, their formation and stability would depend on very specific conditions in the universe. These conditions might include the presence of exotic matter, the right balance of gravitational forces, and even the precise values of fundamental constants like the speed of light or the strength of gravity. The anthropic principle raises the question, could the existence of wormholes be a necessary feature of a universe capable of supporting life? Some theorists argue that wormholes might play a role in the larger framework of the universe's fine-tuning. For example, if wormholes are required to connect distant regions of spacetime, their existence could be tied to the universe's ability to sustain complex structures like galaxies, stars, and planets. Without wormholes, the universe might lack the necessary pathways for matter and energy to distribute in ways that allow life to emerge. This idea also ties into the concept of a multiverse. If our universe is just one of many, the conditions that allow for wormholes might be unique to universes capable of supporting life. In other words, wormholes could be a hallmark of life-friendly universes, making their existence not just a cosmic curiosity, but a fundamental feature of reality itself. Of course, this is all speculative, but it opens up intriguing possibilities. If wormholes are tied to the anthropic principle, their existence could tell us something profound about the nature of the universe and our place within it. Are wormholes a cosmic coincidence, or are they a necessary ingredient for a universe like ours? As we continue to unravel the mysteries of wormholes, the anthropic principle reminds us that the universe is not just a random collection of particles and forces. It's a finely tuned system that allows for the existence of observers like us. And if wormholes are part of that system, they might hold the key to understanding not just the cosmos, but our own existence as well. Next, we'll explore an even more mind-bending idea. Could wormholes be evidence that our universe is a simulation? Stay with us as we dive into the simulation hypothesis and its connection to these cosmic shortcuts. Now, let's take a step into one of the most intriguing and controversial ideas in modern science, the simulation hypothesis. Could wormholes be evidence that our universe is not what it seems, but rather a highly advanced simulation? This theory suggests that everything we perceive as reality might be part of a vast computational framework created by an intelligent civilization far beyond our understanding. And if that's the case, wormholes could play a key role in this simulated universe. Imagine for a moment that our universe is like a computer program running on some unimaginably powerful hardware. In such a scenario, wormholes might function as shortcuts or glitches in the code, allowing information or energy to move between distant parts of the simulation more efficiently. Just as a video game might use portals to connect different levels or regions, wormholes could serve as the universe's way of optimizing its own processes. This idea ties into the concept of computational efficiency. If the universe is a simulation, it would need to conserve resources, and wormholes could be a clever solution to that problem. But how could we ever test such a wild idea? Some scientists have proposed that if our universe is a simulation, there might be subtle clues hidden in the fabric of reality. For example, the behavior of particles at the smallest scales, or the way spacetime behaves near wormholes, could reveal patterns or anomalies that suggest a programmed structure. Wormholes, with their ability to bend spacetime and connect distant regions, might be one of these telltale signs. If we could detect or study them, they might provide evidence that our universe is not a natural phenomenon, but a carefully designed construct. This theory also raises fascinating questions about the nature of reality itself. If wormholes are part of a simulated universe, what does that mean for free will, consciousness, and the laws of physics? Are the rules we observe, like gravity or the speed of light, simply parameters set by the programmers? And if so, could wormholes be a way for the simulation to correct errors or update itself, much like a software patch? Of course, the simulation hypothesis is still highly speculative, and many scientists remain skeptical. But it's a thought-provoking idea that challenges our understanding of existence. If wormholes are indeed evidence of a simulated universe, they could be the key to unlocking one of the greatest mysteries of all. What is reality, and how did it come to be? As we ponder these questions, let's shift our focus to another fascinating theory: wormholes and the cosmic censorship conjecture. Could these cosmic shortcuts challenge our understanding of singularities and the hidden nature of spacetime? Stay with us as we explore this next mind-bending idea. Now, let's turn our attention to a theory that could shake the very foundations of our understanding of spacetime: wormholes and the cosmic censorship conjecture. This idea revolves around one of the most puzzling questions in physics. Are singularities always hidden from view, or could wormholes reveal them to us? The cosmic censorship conjecture, proposed by physicist Roger Penrose, suggests that singularities, those infinitely dense points at the heart of black holes, are always concealed behind event horizons, making them invisible to the outside universe. But what if wormholes could challenge this notion? Imagine a scenario where a wormhole connects two regions of space-time, and one of those regions contains a singularity. If the wormhole is stable and traversable, it might allow us to observe or interact with a singularity directly, bypassing the event horizon. This would directly contradict the cosmic censorship conjecture, which assumes that singularities are always hidden. Such a discovery would force us to rethink not only the nature of singularities, but also the fundamental laws governing spacetime itself. The implications of this are profound. If singularities are not always hidden, it could mean that the extreme conditions at their cores, where gravity becomes infinite and the laws of physics break down, are accessible in some way. This would open up entirely new avenues for exploring the universe's most extreme environments. For instance, scientists could study the behavior of matter and energy under conditions that are otherwise impossible to replicate, potentially leading to breakthroughs in our understanding of quantum gravity and the unification of physics. But there's a catch. If singularities are exposed through wormholes, it could also lead to paradoxes and instabilities in spacetime. For example, the naked singularity, a singularity not hidden behind an event horizon, could create unpredictable and chaotic effects, disrupting the fabric of the universe. This raises questions about the stability of wormholes themselves. Could they act as gateways to these dangerous regions, or would they somehow shield us from their effects? The cosmic censorship conjecture has long been a cornerstone of modern physics, but wormholes present a fascinating challenge to this idea. If they exist and can reveal singularities, it would not only revolutionize our understanding of black holes, but also force us to reconsider the very nature of spacetime. Are singularities truly hidden, or are they just waiting to be discovered through the cosmic shortcuts of wormholes? As we continue to explore this theory, we're reminded that the universe is full of mysteries waiting to be unraveled. With this in mind, let's move on to another intriguing idea: wormholes and the no-hair theorem. Could these cosmic tunnels complicate our understanding of how black holes are described? Stay with us as we dive into this next fascinating theory. Now, let's shift our focus to a theory that intertwines wormholes with one of the most elegant ideas in black hole physics: the no-hair theorem. This theorem, often summarized as "black holes have no hair," suggests that black holes can be completely described by just three properties: their mass, electric charge, and angular momentum. In other words, no matter how complex the matter or energy that falls into a black hole, all other details are lost, leaving behind a simple, smooth object. But what happens when we introduce wormholes into the picture? Could these cosmic shortcuts complicate this clean and tidy description? The no-hair theorem is a cornerstone of our understanding of black holes, but wormholes might throw a wrench into this simplicity. Imagine a wormhole connecting two black holes. If information or matter passes through the wormhole, could it leave some kind of imprint on the black holes, adding complexity to their otherwise simple descriptions? For instance, if a wormhole allows particles or energy to travel between black holes, it might create subtle differences in their properties that the no-hair theorem doesn't account for. This could mean that black holes aren't as bald as we once thought. They might have a bit of hair after all. Another intriguing possibility is that wormholes could act as conduits for information that would otherwise be lost in a black hole. According to the no-hair theorem, all other details about the matter that falls into a black hole are erased, leaving only the three basic parameters. But if wormholes exist, they might provide a way for some of that information to escape or be preserved, challenging the idea that black holes are entirely featureless. This could have profound implications for the black hole information paradox, a long-standing puzzle in physics about whether information is truly lost in black holes or if it's somehow conserved. However, this idea isn't without its challenges. If wormholes do complicate the no-hair theorem, it could mean that our understanding of black holes is incomplete. We might need to revise our models to account for the influence of wormholes, potentially introducing new parameters or even entirely new physics. This would open up exciting new avenues for research, but it would also make the study of black holes and wormholes even more complex. The no-hair theorem has been a guiding principle in black hole physics for decades, but wormholes present a fascinating twist to this story. Could these cosmic tunnels reveal hidden layers of complexity in black holes, or do they simply add another layer of mystery to an already enigmatic phenomenon? As we explore this theory, we're reminded that the universe is full of surprises, and even our most well-established ideas are subject to change. With this in mind, let's move on to another captivating idea: wormholes and the Bekenstein bound. How might these cosmic shortcuts influence our understanding of information in the universe? Stay with us as we dive into this next fascinating theory. Now, let's turn our attention to a theory that bridges the worlds of wormholes and information theory: wormholes and the Bekenstein bound. The Bekenstein bound is a fundamental limit in physics that tells us there's a maximum amount of information any region of space can hold. This limit is determined by the area surrounding that region, not its volume, which is a fascinating concept in itself. But what happens when we introduce wormholes into this equation? Could these cosmic shortcuts challenge or even redefine our understanding of information storage and retrieval? The Bekenstein bound suggests that the amount of information a region of space can contain is proportional to its surface area. This idea is deeply tied to the holographic principle, which proposes that all the information in a volume of space can be encoded on its boundary. It's a mind-bending concept, but it raises an intriguing question. If wormholes exist, could they provide a way to bypass this limit? Imagine a wormhole connecting two distant regions of space. Could it act as a kind of information highway, allowing data to be stored or transmitted in ways that the Bekenstein bound doesn't account for? One possibility is that wormholes could enable information to be distributed across multiple regions, effectively increasing the total storage capacity. For example, if a wormhole links two black holes, the information falling into one black hole might not be confined to its surface area, but could instead be shared or even duplicated through the wormhole. This could mean that the Bekenstein bound, while still valid in isolated systems, might need to be reconsidered in the presence of wormholes. Another angle to consider is how wormholes might influence the retrieval of information. According to the Bekenstein bound, retrieving information from a black hole is incredibly challenging because it's spread out over its event horizon. But if a wormhole connects the black hole to another region of spacetime, could it provide a shortcut for accessing that information? This could have profound implications for resolving the black hole information paradox, as it might offer a mechanism for information to escape or be reconstructed. However, this theory isn't without its complications. If wormholes do allow information to bypass the Bekenstein bound, it could mean that our understanding of information in the universe is incomplete. We might need to develop new frameworks to describe how information behaves in the presence of wormholes, potentially leading to breakthroughs in both physics and information theory. It's a tantalizing idea, but one that requires careful exploration and testing. As we ponder the relationship between wormholes and the Bekenstein bound, we're reminded of how interconnected the mysteries of the universe truly are. From black holes to information theory, wormholes seem to have a way of weaving themselves into the fabric of our understanding, challenging us to think beyond the limits of current science. With this in mind, let's venture into another fascinating theory: wormholes and the holographic universe. How might these cosmic tunnels fit into the idea that our universe is a hologram? Stay with us as we explore this next mind-bending concept. Now, let's shift our focus to a theory that takes us into the realm of the holographic universe, a concept that might just redefine how we see reality itself. Imagine for a moment that everything we know about the universe, every star, every planet, even every thought, is encoded on a two-dimensional surface. This is the essence of the holographic principle, and it's here that wormholes might play a surprising role. The holographic principle suggests that all the information in a three-dimensional space can be represented as a kind of cosmic projection on a two-dimensional boundary. Think of it like a hologram where a flat surface contains all the data needed to create a three-dimensional image. But how does this connect to wormholes? Well, if the universe is indeed a hologram, wormholes could be the threads that stitch this vast two-dimensional tapestry together. One intriguing idea is that wormholes might act as conduits for information transfer between different regions of this holographic surface. In other words, they could serve as bridges that allow data to flow seamlessly across the cosmic code. This would mean that wormholes aren't just shortcuts through space, they might also be shortcuts through the very fabric of information that defines our universe. But let's take this a step further. If the universe is holographic, then wormholes could also be the key to understanding how information is stored and retrieved on this two-dimensional surface. For instance, if a wormhole connects two distant points in the universe, it might also link two corresponding points on the holographic boundary. This could provide a way to access or manipulate information in ways that were previously unimaginable. This theory also ties into some of the most cutting-edge ideas in modern physics, such as string theory and quantum gravity. In these frameworks, the holographic principle is seen as a potential solution to some of the deepest mysteries of the cosmos, like the nature of black holes and the behavior of spacetime at the smallest scales. Wormholes, in this context, might be the missing piece that helps us connect these theories into a unified understanding of the universe. Of course, this is still a highly speculative idea, but it's one that pushes the boundaries of our imagination. If wormholes are indeed a feature of a holographic universe, they could revolutionize not just our understanding of space and time, but also how we think about information, reality, and even the nature of existence itself. As we wrap up this exploration, let's turn our attention to another mind-bending theory: wormholes and the Planck scale. How might these cosmic tunnels exist at the smallest possible length in the universe? Stay with us as we dive into this next fascinating concept. Now, let's zoom way in to the tiniest scales imaginable, where the fabric of spacetime itself might be teeming with microscopic wormholes. This brings us to the Planck scale, the smallest possible length in the universe, where the rules of quantum mechanics reign supreme. At this scale, the universe behaves in ways that defy our everyday intuition, and wormholes might just be one of its most fascinating secrets. The Planck scale is named after Max Planck, the physicist who first proposed the idea of quantized energy. At this unimaginably small size, about 1/trillionth of a trillionth of the diameter of a single atom, the effects of gravity and quantum mechanics become intertwined. It's here, in this chaotic, fluctuating realm, that some scientists believe wormholes could exist, not as cosmic shortcuts across galaxies, but as fleeting, microscopic tunnels woven into the very fabric of spacetime. These tiny wormholes, often referred to as quantum wormholes, are thought to pop in and out of existence almost instantaneously, thanks to the strange behavior of quantum foam. Quantum foam is a theoretical concept that describes spacetime as a frothy, turbulent sea at the smallest scales, where particles and energy constantly fluctuate. In this chaotic environment, wormholes could form, collapse, and reform in the blink of an eye, creating a dynamic network of connections at the heart of reality. But what does this mean for quantum mechanics? Well, if wormholes exist at the Planck scale, they could play a crucial role in how particles interact and how information is transferred at the quantum level. For instance, some theories suggest that these microscopic wormholes might be responsible for the phenomenon of quantum entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, no matter how far apart they are. In this view, wormholes could be the hidden bridges that allow entangled particles to communicate faster than the speed of light, defying our classical understanding of physics. Another intriguing possibility is that these tiny wormholes could influence the behavior of spacetime itself. At the Planck scale, spacetime is no longer smooth and continuous, but instead becomes a jittery, fluctuating entity. Wormholes could act as stabilizers or connectors in this chaotic environment, helping to maintain the coherence of spacetime even as it undergoes constant change. This could have profound implications for our understanding of quantum gravity, the elusive theory that seeks to unify quantum mechanics with Einstein's theory of general relativity. Of course, exploring wormholes at the Planck scale is no easy task. The energies required to probe such tiny scales are far beyond anything we can currently achieve, and the very nature of quantum mechanics makes it difficult to observe these phenomena directly. Yet, the idea that wormholes might exist at this level opens up a whole new frontier in our quest to understand the universe. It challenges us to rethink not just the nature of spacetime, but also the fundamental principles that govern reality itself. As we ponder the mysteries of the Planck scale, let's turn our attention to another fascinating theory: wormholes and the grandfather paradox. How might these cosmic tunnels create scenarios that challenge our understanding of time and causality? Stay with us as we explore this next mind-bending concept. Now, let's shift our focus to one of the most mind-bending implications of wormholes: their potential to challenge our understanding of time itself. This brings us to the grandfather paradox, a classic thought experiment that explores the logical inconsistencies of time travel. Imagine this: you step through a wormhole, travel back in time, and accidentally prevent your grandparents from meeting. If they never meet, your parents are never born, and neither are you. But if you were never born, how could you have traveled back in time to change anything in the first place? This is the essence of the grandfather paradox, and wormholes might just be the key to unraveling or complicating this puzzle. At first glance, the grandfather paradox seems like an insurmountable problem for time travel. If wormholes allow us to move backward in time, they could create scenarios where cause and effect become tangled in impossible loops. But some physicists believe that wormholes might offer a way out of this paradox. One intriguing idea is that the universe has a built-in mechanism to prevent such logical inconsistencies. According to this view, any attempt to change the past would be thwarted by the laws of physics, ensuring that events remain consistent. For example, if you try to prevent your grandparents from meeting, some unforeseen event like a sudden storm or a missed train would intervene to keep history on track. Another possibility is that wormholes don't allow for true backward time travel in the way we imagine. Instead, they might create closed time-like curves, loops in space-time where events repeat endlessly without altering the past. In this scenario, you could travel back in time, but your actions would already be part of the timeline, meaning you couldn't change anything that hadn't already happened. This idea aligns with the concept of self-consistency, where the universe ensures that all events, including time travel, fit together in a coherent way. Some theories go even further, suggesting that wormholes might connect to parallel universes rather than the past. In this multiverse model, traveling through a wormhole wouldn't take you back in time within your own universe, but instead to a different timeline altogether. Here, the grandfather paradox is avoided because your actions in the past would affect a separate reality, leaving your original timeline unchanged. This idea ties into the many worlds interpretation of quantum mechanics, where every possible outcome of an event creates a new branch of reality. Of course, these ideas are still speculative, and the grandfather paradox remains one of the most challenging puzzles in theoretical physics. But the very fact that wormholes could provide potential solutions, or at least new ways to think about the problem, shows just how fascinating and complex these cosmic tunnels are. They don't just challenge our understanding of space, they force us to rethink the very nature of time and causality. As we continue to explore the mysteries of wormholes, let's turn our attention to another intriguing theory: wormholes and the many worlds interpretation. Could these cosmic shortcuts connect not just different points in spacetime, but entirely different realities? Stay with us as we dive into this next fascinating concept. Now, let's venture into a theory that takes the concept of wormholes to an entirely new level, connecting not just points in spacetime, but entire realities. This brings us to the many worlds interpretation of quantum mechanics and its fascinating relationship with wormholes. According to this interpretation, every possible outcome of a quantum event creates a new branch of reality, resulting in an infinite number of parallel universes. But what if wormholes could serve as bridges between these alternate realities? Imagine a wormhole not as a tunnel through space and time, but as a gateway to a different version of the universe. In this scenario, stepping through a wormhole might not take you to the past or future of your own timeline, but to a parallel reality where history unfolded differently. For instance, you might find yourself in a world where dinosaurs never went extinct, or where humanity discovered interstellar travel centuries ago. The possibilities are as endless as the multiverse itself. This idea raises profound questions about the nature of reality. If wormholes can connect parallel universes, could they allow us to observe or even interact with alternate versions of ourselves? And if so, what would that mean for our understanding of identity and free will? Some physicists speculate that such connections might explain certain quantum phenomena like entanglement, where particles seem to communicate instantaneously across vast distances. Could this spooky action at a distance be the result of microscopic wormholes linking particles in different realities? The implications of this theory are staggering. If wormholes truly connect parallel universes, they could offer a way to explore the infinite possibilities of existence, but they also introduce new challenges. For example, how would we navigate a multiverse where every decision creates a new branch? And what happens if two versions of the same person meet through a wormhole? These questions push the boundaries of both science and philosophy, forcing us to rethink not just the universe but our place within it. As we ponder these mind-bending ideas, it's worth noting that the many worlds interpretation remains a topic of debate among physicists. While it offers a compelling framework for understanding quantum mechanics, it also raises questions about testability and evidence. Could wormholes provide the key to proving or disproving the existence of parallel realities? Only time and perhaps a few cosmic shortcuts will tell. With this exploration of wormholes and the multiverse, we're ready to tackle one final theory: wormholes and the ultimate fate of the universe. Could these cosmic tunnels play a role in how our universe ends? Stay with us as we uncover the final piece of this cosmic puzzle. As we approach the final frontier of our exploration, let's turn our attention to one of the most profound questions in cosmology. What role could wormholes play in the ultimate fate of the universe? This theory takes us beyond the here and now into the distant future where the cosmos itself may reach its final chapter. Could wormholes be more than just shortcuts through space and time? Could they hold the key to understanding how the universe might end? One possibility is that wormholes could influence the Big Crunch, a scenario where the universe stops expanding and begins to collapse back in on itself. In this model, wormholes might act as cosmic conduits, funneling matter and energy from one region of the universe to another, accelerating the collapse. Imagine a network of wormholes pulling galaxies closer together, hastening the universe's return to a singular point. This raises intriguing questions about whether wormholes could be both a cause and a consequence of the Big Crunch, creating a feedback loop that shapes the universe's final moments. On the other hand, if the universe continues to expand indefinitely, leading to a big freeze, wormholes might play a very different role. In this cold, dark future, wormholes could serve as lifelines, connecting isolated pockets of matter and energy in an ever-expanding void. They might allow civilizations to survive by transporting resources or even entire populations to regions where conditions are more favorable. But even in this scenario, wormholes would face challenges. As the universe grows colder and emptier, maintaining the stability of these cosmic tunnels would become increasingly difficult, potentially rendering them useless over time. There's also the possibility that wormholes could interact with other cosmological phenomena, such as dark energy or quantum fluctuations, to shape the universe's fate. For instance, if wormholes are connected to the fabric of spacetime itself, they might influence the rate of cosmic expansion or the formation of new structures in the far future. Some theories even suggest that wormholes could be gateways to entirely new universes, offering an escape route if our own universe becomes uninhabitable. This theory forces us to confront the limits of our understanding. While we can speculate about the role of wormholes in the universe's end, much of this remains in the realm of theoretical physics. The extreme conditions of the far future, whether a big crunch, big freeze, or something entirely unexpected, make it difficult to predict how wormholes might behave. Yet, the very idea that these cosmic shortcuts could influence the universe's destiny is a testament to their mysterious and awe-inspiring nature. As we wrap up our journey through 30 mind-bending theories about wormholes, it's clear that these cosmic phenomena are more than just science fiction. They challenge our understanding of space, time, and reality itself, offering glimpses into the profound mysteries of the universe. Whether they connect distant galaxies, parallel realities, or even the beginning and end of existence, wormholes remind us that the cosmos is far stranger and more wondrous than we can imagine. So, which of these theories fascinates you the most? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of space. Until next time, keep exploring the universe because the journey is just as thrilling as the destination. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible theories we've explored about the universe's first wormhole travel. From Einstein and Rosen's early ideas about spacetime bridges to the mind-bending possibilities of wormholes connecting parallel universes, each theory has offered a unique glimpse into the mysteries of the cosmos. We've seen how wormholes could serve as cosmic shortcuts, time machines, or even gateways to entirely new realities. We've pondered their potential role in the fate of the universe, from the Big Crunch to the Big Freeze, and considered how they might interact with dark matter, quantum foam, and even the holographic nature of reality. These theories don't just challenge our understanding of space and time, they inspire us to think bigger, to question the limits of what's possible, and to dream of a future where humanity might one day traverse the stars. The implications of these ideas stretch far beyond the realm of theoretical physics. They touch on the very essence of what it means to explore, to discover, and to push the boundaries of human knowledge. Whether wormholes remain a fascinating thought experiment or someday become a reality, they remind us that the universe is full of wonders waiting to be uncovered. They invite us to imagine a future where the impossible becomes possible, where the mysteries of the cosmos are no longer out of reach. Now it's your turn to join the conversation. Which of these 30 theories captured your imagination the most? Was it the idea of wormholes as time machines, the possibility of traversable wormholes stabilized by exotic matter, or the thought of wormholes connecting us to other universes? Let us know in the comments below. We'd love to hear your thoughts and theories. And if you enjoyed this deep dive into the mysteries of wormholes, don't forget to hit that subscribe button and ring the notification bell so you never miss an update. There's so much more to explore, from black holes to dark energy, and we're just getting started. Until next time, keep looking up at the stars and wondering what's out there, because the universe is full of surprises and the adventure is just beginning.